In this video, we introduce PUP 3D-GS, a pruning technique that drastically reduces the size of pre-trained Gaussian splatting models. This is a joint work by Alex Hansen, Alan Tu, Vasu Singla, Mayuka Jaywardhana, Matthias Zwicker, and Tom Goldstein, appearing at CVPR 2025. Gaussian splatting models 3D scenes with a large set of 3D Gaussians. Throughout this video, I will describe a single Gaussian in this model by GI. This Gaussian is spatially parameterized by its mean, given its 3D location in space, its scale, providing the extent of the Gaussian along three principal directions, and its rotation, giving the rotation in 3D space. The scaling and rotation parameters define the SVD factored 3D covariance. Two remaining appearance parameters are its color, a spherical harmonic vector providing a view-varying color, and its opacity, a scalar providing the opacity of the Gaussian. To represent ground truth poses, I'll use PGT, and for a specific pose, I'll use phi. For a ground truth image, I'll use IGT phi, and for a generated image, I'll use IG phi, where G denotes the set of all Gaussian parameters. The motivation behind PUP3DGS is to score each Gaussian based on how much its spatial parameters are under-constrained relative to the reconstruction error, then prune Gaussians from the scene based on that score. Here I've depicted an extreme example of this. When the dog's tail is only observed by one view, shown on the left, a Gaussian in the tail could be anywhere in the 3D space that projects correctly to the image. If that Gaussian is instead observed by a second camera, it is constrained. Another way to say this is that the L2 error has low sensitivity to the under-constrained Gaussians, a high sensitivity to the Gaussians that are not. Note, this property is second order, or Hessian, a phenomena that is not easy to compute. However, we found a tractable solution for converged scenes. If we start with the L2 error over all training views, we can differentiate it twice to get the Hessian. But when the scene converges, the L1 error approaches zero, and the second order term vanishes. This gives us a full Hessian approximation of the scene, but what we'd like is an estimate per Gaussian. Luckily, we can simply change the gradient to be with respect to a specific Gaussian's parameters. This per Gaussian Hessian measures the sensitivity of the error to the particular Gaussian GI, holding all of the Gaussian parameters constant. Taking the log determinant gives a numerically stable per Gaussian score. However, this per Gaussian Hessian is still quite large. We found that restricting it to the Gaussian mean and scale parameters is sufficient for an effective score. If we start with the trained Gaussian splatting model, we can use our pruning score to prune 80% of the Gaussians, but this results in a substantial degradation in scene quality. However, fine-tuning the scene recovers most scene details. We call this pruning plus fine-tuning prune-refine for short. Surprisingly, we find that we can apply this prune-refine step again, this time pruning an initial 50% of Gaussians. This results in a 90% reduction of Gaussians from the scene while maintaining high image quality. Across scenes, this results in a substantial model size reduction and a surprisingly high rendering speedup. Here's a video result of our approach. On the left is our PUP3DGS method, and on the right is the original Gaussian splatting model before it is pruned. Here are our results again, but this time on an indoor scene. For paper, code, and more video results, visit our website, pup3dgs.github.io. Thanks for watching.